You know, it's like working with my colleagues in the climate science space. It's like going for a run with someone who's faster than you, right? And you get done with the run and you're like, well, I finished. But it seemed like it was a lot harder for me than it was for that guy. And that's the way I felt about writing some of these papers. So, so first and foremost, I'm not a climate scientist, so don't hold that against me. Second of all, I actually used to be fairly technical. I started my career in Microsoft Research, actually, leading research programs at the intersection of environmental and computer science. I did that for about 7 years. But it's been probably at least 6 months, and that's probably being quite friendly to myself, since I've actually written a line of code. And it was brought in stark attention to me this past Monday. I gave a talk at the Space Needle in Seattle. I was asked to come and give a talk to the top 50 computer science students in the United States. And I thought, well, this will be interesting. And so I give this talk. It wasn't one of my best talks, but it wasn't terrible. And one of my close colleagues from Microsoft Research came up to me afterwards, and he's like, man, like, what happened? You used to be pretty technical. And my wife will tell you that that was like one of the most shattered I've come back from any talk. She's like, what happened? I haven't told her yet, but anyway, it's like the ultimate, insult that somebody from your research past can actually level at you. And he also said, you've become quite corporate. So there's that as well. But anyway, we will get into a little bit of technical depth, but quite frankly, a lot of it was my close colleagues in Microsoft Research. And then secondly, look, I work for Microsoft. We're a technology company. I'm going to be talking about the role that machine learning and technology writ largely can help us solve the way that we monitor, model, and ultimately manage Earth's natural systems. That should not come as a surprise to you. I work for Microsoft. So, with that kind of technology industry bias aside, I do just want to spend a few minutes saying that from an issues perspective, I think we're completely aligned. At Microsoft, we actually have this strongly held belief that we as a human society have kind of reached one of our grandest challenges yet. We have to somehow do everything that you guys have been talking about today. We have to figure out how to mitigate and adapt to changing climates, ensure resilient water supplies, sustainably feed a human population rapidly growing to 10 billion people, all while stemming an ongoing and fairly catastrophic loss of biodiversity that's happening globally. That happens to be my background. And so from a corporate perspective, we think about that every day, and we think about our role in it and what we might have to do or to say about that. And one of the reasons that we think that is because we see ourselves as doing business at kind of the intersection of two unprecedented ages. The first is this information age, although that's an exceptionally narcissistic point of view, because when we speak about the information age, it's almost entirely about us. I think most of you understand just how little we actually do understand about the rest of life on Earth. But we're doing business at the intersection of this information age, which we as a company and then our peers in the technology sector really help build the fundamental infrastructure and the architecture, right? But we're also doing in business at in this time of the Anthropocene or Anthropocene or however you want to pronounce it, or whether or not you believe it. There's really no getting away from the fact that we live at a time of rapidly increasing, exponentially increasing negative impacts of human activities on Earth's natural systems. And so what are we going to do about that, and what does a company like Microsoft care about it? And it's interesting for me, one of the reasons I'm still at the company is because some of our senior leaders, this is Brad Smith, the president of the company, they run around saying some things that kind of sound grandiose, but at the end of the day actually do influence the way we as a company think. And what Brad's saying here, for those of you who can't fully parse the corporate speak, is that ultimately, if you believe organizations like the World Economic Forum and others that say that we are starting to enter a new fourth industrial revolution, then you have to look back at history and ask what happened as a result of the past 3 industrial revolutions, right? And what Brad's saying here is that so often each of those 3 industrial revolutions that we have gone through did so, provided the technologies that they did, by borrowing from the future to pay for the present. That's how we got to the environmental state that we're in today, right? So we're not technology apologists by any means, but we do believe that this has to be the industrial revolution, where we stop that cycle, where we break that cycle and we actually start developing the technologies, many of which we've been talking about today, that can allow us to pay for the sins of our past, if you will, as well as plan for a more efficient future. And so we have our president talking about that. We have, folks like our executive vice president of AI and research. I should say that if you haven't been paying attention in the tech sector, we talked about technology, computer technology, then we talked about big data, then we talked about machine learning. Nobody talks about machine learning anymore. Now it's all AI. Everybody's title is AI. And I assume they don't like me because my title doesn't have AI in it. But someday I'll get that promotion, I guess. But here's Harry talking about why we care about investing in AI, and you see that he's bringing up environment from the very beginning. So what I wanted to spend a little bit of time today talking about was, from a Microsoft perspective, where we see the opportunities and some of the difficulties. And I was kind of explicitly asked to talk about this because I was supposed to be on the industry panel tomorrow, but unfortunately have to fly home. And so some of the topics that we would have covered in that panel, I'll cover in this talk. So what are some of the opportunities and difficulties in applying machine learning to climate science? Well, I'm not telling you guys anything that you don't already know, right? Machine learning could potentially fundamentally transform the way that we model climate, right? Who's read the Earth Machine article in Science? Oh man, more people have to read the Earth Machine. Then we can have like controversial drinks and things like that. But right, it's a big funding effort from Paul Allen to go back to first principles from a machine learning perspective through a consortium at Caltech and build a new machine learning based global climate model. So maybe that'll work. We do know that things like using machine learning to plow through and drive insights, we just heard about some of this stuff, from the incredible amount of data that climate models produce is definitely an influence of machine learning that's happening in the climate science community right now. We also know, because people in this room are working on it, that machine learning can help us better perform model integration, weighting the outputs of different models to be able to take the good from certain models while leaving the bad behind. We heard about ensembles in a poster presentation already. And then the last one that I really actually want to talk about, and it's what I spend a lot of my time focusing on every day at Microsoft, is how technology and machine learning based technologies are going to allow us to start taking climate science out of academic journals and government reports and into actionable services and applications that people can actually use to drive better land use and other management decisions every day. And that's really something that, like I said, I focus on every day. And to be clear, I'm not saying that climate science shouldn't be in academic journals and it shouldn't be in government reports. Of course it should be. But I just believe that there's a next step, right, of taking the work that we publish, the models that we publish, the models that we've been hearing about today, and surfacing them up as services that everybody can access beyond just going to your supplemental materials and trying to like ask what in the world that notation system was that you actually used, which is what I was thinking during one of the presentations today. So anyway, those are the opportunities that I want to talk about, and those are the opportunities that really helped influence one of the programs that I lead. I actually lead all of sustainability for the company, so it was super kind of heartwarming during our intro talk to hear NCAR's required conversation about compostables and other issues that this center takes extremely seriously, because I have to focus on those issues as well for our corporation. But another team that I lead is called AI for Earth, and it emerged kind of out of my and all of my colleagues' work inside Microsoft Research earlier, or I guess very late last year in December of 2018, when the company made a 5-year, $50 million commitment to deploying our 35 years of investments in AI research and technologies in the 4 key areas of ag, water, biodiversity, and climate. It was, kind of unprecedented in the tech sector, but more importantly, I think for me, it was unprecedented inside our company to actually take some of this work and just look full across the company and ask how everything that we're doing from a technology perspective could be applied in this space. And so I'm going to talk about the program. You guys might not care about it. I'm going to talk about one aspect of the program that maybe you guys will find interesting. But the way that the program was really set up was to try to create a much more bilingual workforce, right? I think what's interesting is that it might seem like there's a lot of people in this room because it's kind of hot and stuffy and we've all been together for quite a few hours today. But when you step out of this room, suddenly you all become singular almost in your ability to understand both the language of machine learning as well as the language of environmental science broadly and climate science in particular. And AI for Earth really, at its core, is set up to change that, to grow the ranks of the people that are in this room, and not just from a climate perspective, from an ag, water, biodiversity perspective. The first thing that we do is we do something very simple, which is we simply provide access to our technology for free to organizations who work in this space, full stop. Why? It just seems crazy to think that budget would be a barrier to using technology to actually solve any sort of problems. Two, we actually spend a lot of time building up kind of educational curricula to build that bilingual workforce, to be able to take people from the environmental science side, teach them about the latest advances in machine learning and how to use what they have available to them, how to take people from the machine learning community and actually teach them about the problems in environmental science, and that it's actually not just as simple as taking some smart, maybe wildly overpaid, definitely deep learning researcher and throwing them at a problem, right? You've already heard, I think the conclusion of like 5 talks today was deep learning isn't gonna solve all your problems, right? And we should take those 5 people and just like hold a protest outside technology executives' offices, right? With just signs that say deep learning will not solve your problems. I mean, it'll solve some of your problems, but not when they get really hard. You need to know a lot more. You need to do things like starting including physics into some of your feature representations, for instance. I know, crazy idea. And then the last thing that we do, and this is actually what kind of gets me excited every day, is we work really closely both with people inside the company and people outside the company to code together, to build together, to invent together, and ultimately to produce a growing portfolio of what we would call AI for Earth APIs and applications that are available to anybody, anywhere. And that's really where, my ulterior motive and selfish motive of being here is to be able to see all the things that everybody's doing and think, that would make a great service, right? How can I help support that? How can I subsidize that? How can I take your work and make it available to everybody, everywhere? Just really quickly, since December, we started working on growing our AI for Earth grantee portfolio. We have this super simple 2-page, I used to always say we have this super simple 1-page application process, but it's always been 2-page. I just speak kind of with a truthful hyperbole, maybe. And then everybody would email me and say, where's that 1-page application? I can only find it 2. And I was like, well, people are quite literal in the community that I operate in. So we have a 2-page application process. It's extremely simple. If you're taking a machine learning-based approach to any problem space in the 4 areas that we cover, we're looking to support you. In the past 9 months or so, we've grown to about 147 grantees working in over 40 countries, over half of the states in the United States. But you can see that there are still a lot of areas on this map that are not covered, and that is one of my key metrics for this fiscal year, is making sure that we at least double, if not triple, the number of geographies that we represent. And the reason that I think that is so important is because environmental issues manifest themselves so differently in space and time, right? And seeing the way people want to approach those problems helps you understand the true diversity of the problem that we're actually facing. Second thing that we do is we actually hold things like this, only much more hands-on coding and in-depth kind of training, kind of actually not that dissimilar from the hackathon for those of you who joined it yesterday that I heard great things about. I would have gone, but nobody wanted me on their team. So, but we bring people from all around the world together for days at a time. We lock them in rooms, and we teach them, and they teach us. And we help grow this community of people who are all learning from one another. And I hope the Climate informatics community and our Art AI for Earth community can become more closely integrated as time goes on. And then, like I said, everything that we do, from giving out grants to educating people to directly investing in organizations and people, it's all about trying to grow this body of APIs and applications, right? These services that anybody can access anywhere. And so we do that by offering kind of programmatic structure across basically the same structure that the technology industry has followed, right? If anybody is wondering like what the technology sector is all about or what cloud computing is all about or anything else, this is it in 5 simple steps, right? It's all about building the large-scale computational infrastructure that can support unprecedentedly large data sets, that can be confronted with increasingly sophisticated models, that can then be hosted as scalable services that are available anywhere and can be consumed into specified bespoke applications built by people with a specific end user in mind. Full stop, that's it. That's all we do in the technology sector. And so you see, you know, a lot of talk. It's all just talk about this. That's it. And from a climate space perspective, Microsoft's been paying attention to this quite significantly. I think one of the things, I won't go into kind of a full corporate rant about cloud rankings or anything else like that, but the only thing I would say is that from a climate perspective, we're the only cloud, for instance, to have a true HPC deal. We launched a partnership a few months ago with Cray Computing. So now you can have your own Cray computer in the cloud. You can actually have Cray as a service, which might seem crazy to you facing kind of tens of millions of dollars of budget requisition asks to purchase your next Cray machine, for instance. But anyway, we focus on this stack, and then we put kind of programmatic structure around it. So we look at the kind of the machine learning pipeline and we say, okay, well, where are you on it, right? Machine learning is a data-hungry process, right? There's only 2 words, and one of them is learning, and the way you learn is from data. Okay, so in the environmental space, we don't have a ton of data. We have a lot of unlabeled data, but we don't have a ton of annotated data. And that's a big problem. So if you have data sets that are unannotated and you want to annotate them, you can ask us, and oftentimes we'll help pay for that. If you have labeled data and you're struggling to build models, we have teams of machine learning experts that can help you build models. If you have a model, you published a paper, etc., and now you want to make it available to everybody, we have the hosting services. And again, the engineering and other resources to help to host those models as APIs. And if you have an API and you really want to build an application around it, or potentially more importantly, you already have an application that lots of people are using, and this is where we've been investing quite significantly over the past couple months in, then we want you to be running that on our infrastructure. We'll help you abstract out a bunch of your climate or more broadly environmentally based services, and we will help you stand those up, stand your application up, and subsidize the whole thing as we go. And you know, we offer those things up. I don't know, for those of you who saw GitHub and Microsoft have just become a lot closer with our acquisition. And so we take everything that we do, we seek to sign licenses that put everything that we do in the public domain as truly open source. So we're not looking to take this and lock it up inside the vaults of Microsoft. We say that we invest on behalf of the planet and on behalf of Microsoft, right? So we put it out there first, and then we work with you down the line. But we open source the code, we put it out there. We open source the models, we put them out there. We subsidize, as I said, the use of the applications and data APIs. And we just look to get people to be thinking about how machine learning can actually help in these spaces. I mean, in many respects, most of the talks I give are not to communities like you, right? Most of the talks I give, I'm trying to explain to people what machine learning is, right? I don't need to tell you guys that, but what I do think I do need to get through to you a little bit is the importance of taking what you're doing and getting it more broadly available to communities of people who want to use it. And so I just want to spend a little bit of time talking about one application area that that we've been working on and has been motivating kind of our deep learning experts. Actually, one of the most satisfactory emails that I got since AI for Earth was launched was from the lead machine learning researcher on this project. And I remember going into his office well over a year ago and talking about this problem and him saying, that should be easy. Don't worry, yeah, just give it to me, I'll send you something this weekend. And the email today was, well, I guess it's true, this is a non-trivial problem. And anyway, so I'll take my small victories. But to be clear, a lot of this stuff is hard, as you know. Trying to actually make advances in this space is hard. And one of the places that we wanted to advance the national conversation was around land cover mapping. Because here in the US, and most of you already know this, but if you don't, here in the US, one of the most technologically advanced economies on Earth, right? What we know about our national landscape is minimal. Our ability to understand what is where, how much is there, and how fast is it changing, which is basically what everybody's talking about trying to do today, we know basically nothing. We have a few maps. The latest map of where our forests and our fields, our agricultural lands, and our urban areas are is about 8 years old, right? I had hair 8 years ago, right? And that's not the only deforestation that's been going on in the United States. So, and it's 30-meter resolution. I know a lot of us, almost all of my papers have the word global in the title. Why? I don't know, it's easier to get published when you do that. But also, you don't have to zoom in and focus on where things are wrong or how actually what you found doesn't really matter because it doesn't zoom in. It doesn't resolve itself to the locality of the problem, right? So it's great from an academic perspective. It's not great from an applied perspective. And so we have this map, and zoomed out, it looks pretty, right? This is the NLCD data set put together by the US government using Landsat 30-meter resolution data. This is 2011, the last version of this data set. And as you can see, as you zoom into a particular part of the United States, this is the Chesapeake Bay watershed, which many of you may already know. And if you don't, we'll be talking about it a little bit more moving forward. You can see that when it gets down to actually thinking about things at like an urban or an exurban or a rural scale, like understanding these, you know, it might be great in the middle of a national forest when it's all trees, but when you're looking at places where there's a relatively high heterogeneity of land cover classes, spatial and temporal resolutions like this just don't get you very far. And instead, what we wanted to do, and with partners whom I'll talk about in just a moment, is we wanted to change the spatial and temporal resolution with which we were able to understand what is where, how much is there, and how fast is it changing in this country, right? We wanted to, in pictures, go from this 30-meter resolution map that's 8 years out of date to that 1-meter resolution map, which is a year old, right? And the question is, how are you actually going to go about doing that? And again, we work at Microsoft, so we thought we'd take a machine learning approach. Whether or not that's the right one, who knows? But what we did was, oh, that was tricky. Our partner's logo just faded in and out. Did you see that? Oh, perfect. There, it's back. All right. I do love the Chesapeake Conservancy. What we wanted to do was what I just said, and so did a small organization called the Chesapeake Conservancy, which works to protect the lands and waterways of the Chesapeake Bay region, right? Chesapeake Bay region, when you zoom out from a national scale, is pretty small. But when you think about it from being on the ground, it's still pretty big. It's about 100,000 square miles, right? And they wanted to build the first 1-meter resolution map so that they could actually help make precision management choices. They wanted to be able to understand not just that like this side of the bay needed help,
but this agricultural field was contributing to runoffs. This is where you should plant not just trees, but a tree, right? To be able to mitigate some of the issues in the bay. So they took about 2 terabytes of aerial imagery from another national government program called the National Agricultural Imaging Program. Has anybody used that data set in any of your work? No? A couple people? Here in the US, we have freely available 1 meter resolution, annually updated imagery that we fly with planes, which is cool, but then you say it and it kind of sounds outdated. But we fly planes every year across the United States acquiring this imagery. And they took a relatively kind of old school approach to making this map, and it took them 18 months to produce a 1 meter resolution map of the region. We acquire imagery every year, so that meant that by the time they got done and they had spent well over $1 million, their map was already out of date. And starting again was going to take them another 18 months, right? So the question was, well, how do we break that cycle? How do we help them actually get ahead? And this is the map that they created. So this is the size of the Chesapeake Bay watershed. And the size of the map that they created. This is the kind of the accuracy. It's actually fairly impressive, particularly when you consider the amount of pixels that they actually had to plow through. Because remember, when you're talking about a 1 meter resolution map, for instance, of the entire United States, you're talking about something like 10.5 trillion pixels that you have to do inference over, right? So it's one of the reasons that it took them a long time. Anyway, like many people, we thought, why not take a deep neural network approach? And particularly, why not take a deep convolutional neural network approach, which might take advantage of some of the scale invariant properties of imagery, for instance, because that's what everybody else does when they try and identify cats in YouTube videos, for instance. So that's what I'm going to be talking about. And all we wanted to do was something super simple, right? We wanted a flow chart like this. We wanted to take some labeled training imagery. We wanted to use the map that it took them 18 months to create as annotated data. We wanted to train up a model. We wanted to serve that up and allow anybody to feed in new imagery from around the country and get results. That was it. That's simple. That's all we wanted to do. It turns out, of course, that that's really hard for a lot of different reasons. One, it's because there's multiple different data sets that you have to deal with. They're flying this mission with different planes, with different sensors at different times of the year. And you'll see how that changes a lot of the image quality, et cetera, et cetera. And so fundamentally, I also like to think just because it's more beautiful, but Seattle, the Pacific Northwest, does not look like the East Coast of the United States when you look down in aerial imagery. It just looks better, quite frankly. And it's a huge geographic area. We already covered this, 10.5 trillion pixels. And it's varied. The land classes that you find in one place aren't the land classes the other. And man, if you ever want to see me get up and leave a meeting quickly, it's when you start talking about ontologies, right? And data structures and things like that. So anyway, but it's complicated. What classes do you actually use? What's that minimum common denominator of classes? We have lots of different years of data sets. The data sizes are completely different. When you add it all up together, as we'll talk about, it's something like 55 terabytes of data just for this one simple kind of problem. And the competition data sets that are out there aren't that good. And that's one thing to remember, which is how did we get where we are from a machine learning perspective in imagery or anything else? It's because the computer science community and the technology industry all rallied around a few common data sets for training as benchmarks, and we could compete with each other, and we knew if we were doing better or worse than our colleagues and better or worse than last year. Think about things like ImageNet, for instance, and the fact that basically everything that we've done in computer vision, at least that we're shipping, these days, has predicated on work that started on ImageNet, right? Well, the competition data sets in land cover classification, there's about 4 or 5 of them. They're not that great. They don't cover a lot of space, and they're not that representative. And so what we ultimately ended up doing was taking an approach that used multiple different data sets This is the National Agricultural Imaging data set on the top row here. So this is 1 meter resolution. You can see already some of these problems. This is 2012, and that's 2015, the exact same space. That image looks fundamentally different, right? And it's something that we're still getting better at in dealing with from a computer vision perspective. These data sets are collected annually. Then we have one annotation data set that we can use to train. We could simplified it down into 4 just to make our jobs as easy as possible: water, forest, fields, and impervious surfaces. So we have one training data set in one part of the country. We have nationally other data sets over many different years. And then we also have these Landsat-based images for the country. Landsat's collected every 2 weeks or so, I think. Maybe we just got that terribly wrong, but it's a 30-meter resolution, and that gives us an opportunity to be able to do things like comparing leaf-on and leaf-off imagery, which makes images, again, of the exact same place look very different. And in this case, we also have an annotated training data set that was collected about 8 years ago, and before that, about every 5 years. So the question was, how do we actually put that all together? Oh, sorry, there's one more thing that I just want to highlight. So NAEP imagery comes in RGB-IR, right? So we've got 4-class imagery coming in, and here's the NAEP pixel values, right? For these different categories that have been classified in the annotated map in different locations. And you can see that as you go to different places, what deciduous forest looks like from a pure RGB-IR perspective changes fundamentally. Those distributions are all over the place. So you need to learn a model. That can work in one part of the country, and then jump over to that distribution and get that right as well. It's not that easy, it turns out, as that guy emailed me today. But just really quickly, what we did. So we took kind of a standard, for those of you who have been paying attention to the vision world, the UNet architecture has kind of taken the world by storm, and we took advantage of that. We take these 4-channel RGB-IR image patches as input, and all we want to do is predict probabilities, 4 output classes at each pixel. And then we start getting a little bit fancy, because just doing that doesn't actually work that well. So we do a bunch of data augmentation. There's really 4 kind of key types of data augmentation that we do in this model. We include 30-meter resolution Landsat, both leaf-on and leaf-off. We also include a specialized, what we call super resolution loss function from the 30-meter resolution 8-year-old NLCD data sets that kind of give us some sort of prior information about what maybe should be there in a 30 by 30 pixel that we then have to predict at a 1 by 1 resolution. We take many years of our NAEP imagery from an augmentation perspective, and then we do all sorts of different color augmentations. And in the Chesapeake Bay region where we train this model, we do actually pretty well. On average, we're about 90% accurate, both on train and test. But it's a lot more complicated than that. First of all, I'm kind of cheating here because I just added everything together, and there's a lot of forest. And just getting forest right in the middle of forest isn't all that impressive. In fact, just random expectation in the middle of forest would get you there, right? So, so even I could write a model that would do that. But the other thing that's interesting is we don't actually have ground truth, right? And this actually came up a little bit in a conversation after one of the past talks, which is we have modeled output as ground truth. And we know that is only so accurate, and is in some cases, for some classes, down into the mid-70s. So when we're wrong, are we really wrong, right? Or are we just wrong against something that was already wrong? In which case, maybe we're right, right? Now you can see how, like, I have my meetings with my manager every day. She's like, you should do that differently. I'm like, should I? I mean, there's a couple ways to see it. But the end of the day, by doing that, by taking those data augmentation approaches, ended up with 55 terabytes of input, 25 terabytes of output. It took us a week to perform inference across the entire United States on 40 K80 Tesla GPUs. So not crazy. One of the things that's great is it's easily parallelizable. We're Microsoft, so if we want to, and we have, we can throw 1,000 GPUs at it or 10,000 GPUs, and we can just drop that number way, way down. And it all works, so that's great. And then the thing that you have to realize from our perspective of going from that, like, hey, we have a national land cover map that nobody anywhere actually wants to use, to having a national land cover map that everybody everywhere wants to use, means that you have to be able to zoom in and help people correct some of the systematic biases that the algorithm produces in any particular geographic location. We worked with the Chesapeake Conservancy to do exactly that. So here you can see the NAPE imagery. This is the input imagery. The second panel over is the raw output of our model. To just kind of human eye, that looks pretty good. But organizations like the Conservancy, they care about down to the meter. They care about where they should put a tree, not where they should plant a forest, right? And so what we did is we worked with them for this entire region, which is about 6,300 square kilometers. We asked them to do Q&A over 1% of that region. That's all, just 1%. Don't spend forever, spend a week, we said. So they came back after 30 hours. They'd done some Q&A, and they ultimately ended up annotating or changing the annotation of about 2% of the pixels that were in that 1% of 6,300. So you can do the math pretty quickly there of how much they actually did. But then we can learn from their annotations to reweight the model for the entire region. And by doing that, we corrected over 90% of the systematic model errors across the entire region, right? We got the map to something that they would actually use, and we saved them if they had gone through this process. I love setting up straw man arguments, by the way. Almost 3,000 hours of work, right? Whether or not they would have ever spent 3,000 hours of work doing that is a separate question. And then we asked another question, which is, okay, but that still took a week with a bunch of K80s. Sure, we're Microsoft, but we can spin stuff up. But like, what's the fastest we could do this, right? So this is a little bit of apples and oranges because we actually had to step down in model complexity. This is a much more simple ResNet 50 model that we're running, just based because of the product readiness when we did it. But we took advantage of a different approach in Silicon and in Azure that we've been taking that we think differentiates us pretty significantly, which is that we've made a big bet on FPGAs, right? Or if you're field programmable gate arrays. So now if you come to Azure, you've got your CPUs, your GPUs, your FPGAs, your crays, and if you believe some of our colleagues, which I do, someday we'll have your quantum computers as well. So the question is, how do we take advantage of these FPGAs that we have in Azure, which allow us to do specialized computing very quickly and in a reprogrammable way, and how do we do machine learning on top of those FPGAs? Well, we recently launched a product called Project Brainwave that instantiates a lot of popular machine learning frameworks on top of FPGAs. And we brought our land cover mapping problem to this space. And we wanted to see kind of how fast we could go and how cheap. So we spun up 800 of these cores, and we fed in the 200 million images that we had. It's about 20 terabytes of data when we simplified the model down. We experienced about 1.8 milliseconds latency per read. And we managed to plow through the entire United States and produce a national land cover map in 10 minutes. For $42, right? And that's the kind of difference, the difference between 18 months and well over $1 million to 10 minutes and $40 that we're trying to drive to in all sorts of different applications. And then that's just kind of proving that our model actually kind of works. The real reason that we did it is we wanted to then be able to take that model and stand it up as a service, right? And so we can do that in multiple different ways now that we've stood up our land cover mapping model as an API in the cloud. One way that we can do it is by integrating it into popular third-party software applications. So who here uses Esri's software? A couple people, right? And so it was simple enough to simply plug in our model into their software and allow people to zoom anywhere around the country, real time, view the National Agricultural Imaging imagery, which we're showing in the upper left, that Esri hosts, view any other data set that they might have. This is in Oakland County, Michigan, where the county had actually invested in a 1-meter resolution land cover map themselves about 7 years ago. And you can see instantly from the image on the over here that intersection has changed completely, right? It went from a T intersection to a roundabout. And just by scrolling around, you can see that's the hard max and soft max predictions out of our model, that we're able to update that land cover map in real time using our GIS software. We're able to, as well, build just simple browser-based applications where we can actually go and do that and allow people to cruise around and actually see how it works in real time without any kind of third-party software. So I'm going to do what I was taught never to do and try to do a live demo. Don't do this if you're a PhD student. If you're a tenured faculty, you can do whatever you want, right? But if you're still on the job market, don't let yourself get video doing a live demo that's going to be put on YouTube. But let's see, where should we go? Let's go where this thing was. Let's go where this thing grew up. I love talking about machine learning algorithms like they're like people, because we already started doing that by saying that neural networks are like our brains, even though they're not. Is this going to work? Come on. Oh my God. Okay. Perfect. So you can see that, well, let's actually switch to, one of the things that I think is amazing is that this application was actually built by an intern. In fact, let's be honest, no researchers actually did this. All the interns did all the work anyway. But these are machine learning interns. They're not engineers or software developers, but they can build some simple stuff, right? And now we have an application that the entire team uses to be able to cruise around and look and see how well this system works. And one thing that's just interesting is to kind of, you can zoom around and let's actually see how it does with like some changing things. You can see we can pick up structures like docks. Let's see if we can pick up vessels, kind of. And so what we end up doing is we go around and we use this tool to constantly improve our algorithm. We go around and we can now ask questions. We're not just looking at confusion matrices of like, oh, that's interesting. It mixes up forests and fields. Because it mixes up forests and fields differently in different parts of the country. And for us to be able to do that, we need tools like this to be able to dive into the internals of the algorithm and actually figure out what it's getting wrong, where, and why. So there we go. I was going to do more of a live demo, but I made myself nervous. So that's that. And what I'm going to try to do is get us back on time, actually, because I'm going to finish. And all I wanted to say is pretty simple, that what I've seen today and my interactions with the climate informatics community over the past year is phenomenal. I see an extremely committed, diverse, and geographically diverse, and institutionally diverse group of researchers all focusing on taking a machine learning first approach to climate science. That's what we're trying to do. And to the extent that the AI for Earth program can assist the work of the climate informatics community, we're completely up for those conversations, as long as everybody else is up for the ultimate goal of empowering everybody everywhere to be able to start including the results of your climate science in policy-based decisions on the ground where it matters most. And so with that, I'll just say thank you and encourage you to visit our website if you are at all interested in joining the AI for Earth community, applying for one of our grants, and beginning kind of the journey of working with some of our researchers and engineers. So thank you very much.